In the previous lecture, we had discussed the concept of a point source of heat, okay, with source strength Q. Okay. So, this was defined by this equation. Okay. K times the Laplacian of t plus q into delta of x is equal to 0. This is a point source that emits heat q per unit time from the origin. Okay. This delta function is non-zero only at x is equal to 0. It is 0 whenever x is not equal to 0 and the integral is 1. And by integrating this, I showed you that you get the same result that you would get for a sphere of finite size, except that this sphere is now of infinitesimal dimension, and therefore, the heat flux and the temperature both diverge as you go towards the origin. Okay. So, this is an idealization of a source of heat in the limit where the distance from the source is much larger than the size of the source. Okay. In that case, you can consider this to be of infinitesimal dimension. And we had derived what was the temperature field due to the source and the heat flux due to the source. And I had shown you that this corresponds to n is equal to 0, m is equal to 0 in the spherical harmonic expansion. Okay, it corresponds to n is equal to 0 and m is equal to 0 in the spherical harmonic expansion. Okay. And I should, there is a mistake here, it should be q. Okay, q by 4 pi k. Okay. So, from that we got the expression for the temperature and the expression for the flux. Okay. Now, if that source is not at the origin, but at some other location x s, the source location, then I just shift the origin there, determine all distances from the source location. The distance becomes just x minus x s rather than x itself, okay, and the temperature equation and the equation of the flux remain unchanged. Okay. The flux is along the displacement vector from x s to x, and the temperature is given by q by 4 pi k into the distance. Okay. The advantage of representing this in terms of a point source is that you can use it even when you have multiple sources. Okay. At the observation point, you just add up the temperature due to each individual point source, and at the observation point you can just add up the fluxes. The fluxes are vectors, so you have to add them up as vector sums, or you have to add up the components of the fluxes. Okay. So, that is a simple extension of this concept of point source to multiple sources. Okay. So, next let us examine what is called a point dipole. Okay. Okay, so, let us define it a little carefully. Okay. Let us say that I have a source of strength plus q, okay, and a sink of strength minus q, okay, a sink of strength minus q separated by a distance L along the along the z axis. Okay. Okay. So, this one is plus q and this one is minus q. Okay. And if I am considering the temperature at some observation point x, okay, in such a way that the length distance separating the two is much smaller, than the location of the observation point x. Okay. In that case, what is the temperature? Okay. So, the source location is 0, 0, L by 2, okay, which is, I will call it as x plus, okay, and sink location 0, 0 minus L by 2 is equal to x minus. Okay. What is the temperature field due to this combination? Okay. So, the temperature field is going to be equal to Q by 4 pi k into x minus x plus minus Q by note that the amount of heat emitted by the source plus Q is equal to the amount of heat absorbed by the sink minus Q per unit time. So, therefore, there is no net source of heat in this particular case. Okay. I have a source and a sink that are close to each other in such a way that the net source is equal to 0. Okay. So, what is this distance? Okay. X minus x plus is equal to square root of x square plus y square plus z minus L by 2 the whole square. Okay, so, x square plus y square plus z minus L by 2 the whole square. I can expand this out as square root of x square plus y square plus z square minus L z. Okay. Let me call this as L z. Okay, I will put a subscript on z on this one. Okay, so, this will be okay. So, this will be L z by 2. Okay. Okay. Plus L z and I can take a common factor of x square plus y square plus z square out. Okay. Okay. Using the in a spherical coordinate system, this r square is equal to x square plus y square plus z square. Okay. So, I can take, if I take the distance from the origin as r, then r square is equal to x square plus y square plus z square, that is the coordinates of the location of the observation point. Okay. So, I can write this as square root of r square minus L z plus L square by 4. Okay. Take a common factor of r outside, okay, 1 minus L z by r square minus L square by, should put L z everywhere. And since we are considering the limit where Lz is very small compared to x, which is basically equal to the distance from the center, I can use a binomial expansion here. Okay, I can use a binomial expansion here, and this will be equal to r into 1 minus Lz z by r square, 2r square. Okay. Okay. Plus Lz square into r square minus z square by 8 r power 4. Okay. This is the binomial expansion of 1. Okay. Recall that 1 plus x whole power half is equal to 1 plus half x plus half into minus half by 2 factorial x square plus etc. Okay. So, just implementing this binomial expansion, you will get this expression. Okay. I will leave this as an exercise for you. Note that you have one term that is proportional to Lz times z by r square, the other term is Lz square by 4r square. Okay. So, you have two terms here, and expanding these terms you will get a binomial expansion. Okay. Okay. Now, in this term here I have 1 over x plus x minus x plus. Okay. So, I have to take inverse of that. Okay. Okay. This will be equal to 1 over r into 1 minus L z by 2 r square plus and this also I can expand out in a binomial expansion, and I will get this as 1 by r into 1 plus Lz z by 2 r square, okay, plus 3 z square Lz square by 8 r power 4 minus Lz square by 8 r square. Okay. That is by doing the expansion. Okay. This expansion now is of the form 1 by 1 plus x is equal to 1 minus x square plus 1 minus x, okay, x power minus 1. So, plus x square by 2 minus etc. Okay. So, this using just this binomial expansion, this is what you will get. Okay. So, that is for this first term here due to the source. Okay. This is for the first term due to the source. Okay. The second term is due to the sink. Okay. Recall that 1 over x minus is equal to 1 over x square plus y square plus z plus L z by 2 the whole square, okay, whole to the half. Okay. I guess write it again. compare that with the expression that I just had, okay, for 1 over x minus x plus, okay, is equal to 1 over x square plus y square plus z minus Lz by 2 the whole square whole to the half. Okay. The only change here is the sign of this Lz. Okay. So, I get the solution for 1 over x minus the distance from the sink location by just changing the sign of Lz in the distance for the source location. Okay. So, this will just be equal to this same expression that I had here, except that the sign of Lz changes. Okay. The sign of Lz changes, that is the only difference. Okay. So, therefore, I can get the temperature field. Okay. T is equal to q by 4 pi into k into 1 over x minus x plus minus 1 over x minus x minus. Okay. So, therefore, I take this first term here, the source term, and I subtract out the sink term. Okay. You can easily verify that the terms that are either independent of Lz or proportional to square of Lz will cancel out when you subtract out these two, and the only term that will be left is the term that is linear in z. Okay. Q by 4 pi k into Lz z by r cubed. Okay. So, that is the solution for the temperature field for a point dipole, which is a combination of a source and a sink separated by a small distance Lz. The temperature at the observation point, where the distance from the source and sink is much larger than the separation of the source and sink, is q by 4 pi k into Lz into z by r cubed. I can also substitute in here z is equal to r cos theta for a spherical coordinate system. I will get q by 4 pi k into Lz cos theta by r square. This was for two points that are separated by a distance Lz in the z direction. Okay. So, this was for two points that are separated by this distance Lz in the z direction. Okay. Nothing special about the z direction. If I did the same calculation for the x and y directions, okay, I would get similar results. Okay. So, recall that in this case the temperature field was T is equal to q, okay, Lz z by 4 pi k into r cubed is equal to q Lz cos theta by 4 pi k r square. Okay. I can do the same calculation in the x and y directions. Okay. Okay. I can have a source and a sink. I can have a source and a sink separated by a distance Lx in the x direction. Okay. Okay. And I have an observation point x over here, and I am calculating what is the temperature due to the combination of the source and sink separated in the x direction on the observation point. That one will be equal to q Lx x by 4 pi k r cubed. X is r sin theta cos phi, so is equal to q Lx sin theta cos phi. Okay. A straightforward extension. Okay. And the other possible separation is in the y direction. Separated by distance Ly, observation point x, distance r. Okay. The temperature will be equal to q Ly y by 4 pi k r cubed. Y is sin theta sin phi. If the temperature field is due to a combination of these sources and sinks, then I can write T is equal to Q into Lx x plus Ly y plus Lz z, okay, which is equal to Q into L vector dotted with x vector. So, the temperature field due to a point dipole, source and a sink of equal magnitude, okay, separated by an infinitesimal distance L vector, such that this combination Q times L is finite. Okay. Okay. Q goes to infinity, the separation goes to 0 in such a way that Q times L is finite. Okay. In that case, you get a dipole field which is equal to, okay, the dipole moment dotted with x by 4 pi k r cubed. Okay. So, this is equal to this q L is a vector, okay, dotted with the position x. Okay. That is the dipole term. Okay. In this case, the temperature decreases proportional to 1 over r square, as you can see over here. Okay. As you can see over here, the temperature decreases 1 over r square, okay, for these dipole terms. Okay. When I express the numerator also in terms of r and the denominator in terms of r, ultimately the temperature decreases as 1 over r square. For a point source, we had seen that the temperature decreases as 1 over r. In this particular case, there is no net source because there is a source plus q and a sink minus q. whatever comes out of the source goes back into the sink. So, there is no net source. So, if you are sufficiently far away from the dipole, the temperature field cannot decay as 1 over r because there is no net source, and therefore, the temperature field decays as 1 over r square in this case. And this is the temperature due to a point dipole, and the dipole moment is q times L. Okay. Back to our temperature expansion. Okay. We had seen that the term n is equal to 0 is the point source. Next is n is equal to 1. Okay. N is equal to 1 implies that the temperature is equal to A11 r plus B11 by r square, okay, Y11 of theta and phi, okay, plus note that n is 1. So, m has to be 0, 1 or minus 1. Okay. These three terms decreases 1 over r square, okay, which is identical to the decrease that we had for a point dipole. Okay. Y10, okay, you recall Y10, okay, we had written down y is equal to, yeah, okay. Y10 is proportional to z over r here. Okay. Y10 is proportional to z over r, y1 minus 1 is x minus iy over r, and this one is x plus iy. So, we will just express it in terms of that. Okay. So, this will be equal to A10 r plus B10 by r square, okay, to a constant times z by r. Okay. The constant is for normalization, but that constant can be incorporated into this A10 and B10, okay, plus A11 r plus B11 by r square into x plus I y by r plus A1 minus 1 okay. So, recall that our point dipole, okay, in the z direction was q Lz z by 4 pi k r cubed, okay, which is exactly this combination, okay, z by r cubed times a constant. So, for n is equal to 1, the decaying term decreasing proportional to 1 over r square for n is equal to 1 and m is equal to 0. Okay. So, this is for n is equal to 1, m is equal to 0. This is exactly the same as the point dipole with separation in the z direction. Okay. in the x direction, okay, q Lx x by 4 pi k r cubed. Okay. That was the separation in the x direction. This can be written as q Lx by 4 pi r square into y 1 1, okay, plus y 1 minus 1, okay, by 2. Okay. Okay. So, if I take a combination of these two, okay, y 1 1 and y 1 minus 1 by 2, I get x, okay, and that is what I have over here. Okay, that is what I have over here. Okay. So, the combination of minus 1 and 1 for m in this case, if you add them together, you get a point dipole separated in the x direction. Okay. And if you subtract them out, you will get a point dipole in the y direction. Okay. So, q Ly y by 4 pi k r cubed is equal to q Ly by 4 pi k r square. There should be k here. Into y 1 1 minus y 1 minus 1 by 2i. Okay. Subtract out the complex conjugate, divide by 2i, and that is a separation. So, these three terms for n is equal to 1 in the spherical harmonic expansion correspond to sources and sinks separated respectively in the z, x and y direction in such a way that the source energy emitted per unit time goes to infinity, the separation goes to 0, and the product q times L is finite. In that limit you get a point dipole, okay, which the three solutions for the point dipole are for the three vector separations in the x, y and z directions, okay, for n is equal to 1 and m is equal to minus 1, 0 and plus 1. Okay. So, combination of these correspond, linear combinations of these correspond to dipoles with separation in the x, y and z direction. Okay. So, this is the physical interpretation of the point dipole. Okay. So, I will continue this in the next lecture, where I will specifically address the issue of what these terms mean. Okay. I told you what is the terms that decrease proportional to 1 over r square, what they mean. I will address what these first terms mean. Okay. I will continue this in the next lecture. I will see you then.